Very good afternoon, all present. My name is Anmol Krishan Sachdeva, and I'm joined with my colleague Samrat. We are going to talk about declarative device virtualization. We gave a similar session at the Open Source Summit 2 days back. So we are going to create a new flavor of that particular talk and share some other insights as well based on the FAQs, etc., that were asked in that conference. Just a disclaimer that the content which we'll be talking about is purely based on our own interest areas. This is not going to represent any of the organizational views, etc., even for professional bodies that we are associated with. So the agenda of the talk is as follows. We will be first understanding what all the pitfalls are there when we are using GPUs for hardware acceleration, etc., and any kind of advanced processing that we need to do. Then we will be getting into some of the strategies as to how GPUs can be shared. We then will be getting to know about a particular project called HAMI, which will allow you to have more control over GPU sharing. We'll then be talking about dynamic resource allocation, which is set to get GA in 1.34 Kubernetes version. And then we are going to talk about some of the next steps that you can take from advanced GPU-based scheduling. So first thing that we need to understand is that whenever we are talking about any AI ML workloads or even some numerical or scientific workloads, we need to have a lot of processing power. That processing power can come from either CPUs or GPUs depending on the workload that you are training. Specifically, when we are talking about GPUs, we need to understand that Kubernetes doesn't have a native native way to have GPUs treated as similar to how CPU and memory are there. So CPU and memory are indivisible, are divisible resources. You can actually have fractional CPU requested or memory requested. But when you talk about GPU generally is always requested as an integer. So you will request either 2 GPUs or 3 GPUs or 1 GPU, but you cannot have 1.5 requested or let's say 40% of GPU requested, etc. This is where GPU is an indivisible or a resource which cannot be allocated in fractional manner just with the native Kubernetes capabilities that we have. The other thing is that because of this fractional issue that we have, generally you end up having resources scheduled for GPUs, and applications really require some really small amount of those resources. So like you could be having 20% resource requirement for your GPU, but you have allocated 2 GPUs or 1 GPU, then it just means that it's going to be underutilized and you are ultimately going to waste a lot of money, and it's going to also have cost and FinOps effects. So this is how you generally request for a GPU. You will be specifying this in the limit of your resources, and you will be having 1 GPU, let's say, requested. And as I mentioned, the idle GPUs that are there, they just burn your money. And generally, when you are constrained on hardware, just allocating multiple GPUs to the same application or going ahead with, let's say, 10 applications requesting 20 GPUs won't really solve any purpose, because it might be that your workload's nature is dynamic, and you could be then having some auto scaling done, because of which you could be requiring 10 extra pods to come. Those 10 extra pods, when they will be requesting for additional GPUs, you will be already running on exhausted capacity, so you won't have any GPUs to give to those additional 10 pods whenever your workload is scaling, and hence ultimately you will be having your pods kept in pending state. So this is where we get to know about some of the strategies that are there. Before we got some advanced GPU based schedulers that came into existence. So NVIDIA MEG is something that got launched around 4 to 5 years back. This is multi-instance GPU. This is where you have a hardware isolation practiced, wherein one GPU can actually be sliced into 7 instances. These 7 instances are actually configured at the hardware level. So you can just assume that out of one GPU that you have, now you have compartments that are memory isolated, that are isolated from cache perspective. So you have proper fault tolerance, memory isolation, cache isolation, etc., getting exercised whenever you are using such kind of architecture. So as I mentioned, there are some specific guarantees that you get because of this kind of architecture, so the quality of service really gets high. And hence, this is a preferred approach if you have multi-tenancy ecosystem wherein you want multiple applications who want small GPU amounts to be allocated. They can actually go ahead and request for MIG. So this is an example wherein we can request for 1 GPU with 10 GB of memory. So this is the GPU memory that I'm talking about. This is not the CPU memory. But there are pros and cons with every approach that we will be talking about. So the pro is one of them. We have seen quality of service is one. The other is that it's actually giving you multi-tenancy isolation. However, the cons are that it's a bit of inflexible, I would say. If at all there are any configurations that are to be redone, then in that case you just need to go ahead and reload the GPU. Now the question in the previous talk we got asked was whether it's really required to reload the whole GPU or whether it's okay to just go with the driver reload. So the answer is that you can actually go with driver reload, GPU reload. A full reload will actually be required if at all there will be any kind of errors at the XIG state, or there are any specific memory corruption related issues, or let's say your driver version has got upgraded or BIOS firmware has got impacted. Then in that case, you will be requiring a full reload, else just a driver reload using a utility like a system management interface from NVIDIA SMI will actually do. So this is how it looks like. Let's assume this is your GPU. You have 7 compartments here in terms of GPU slices. So this is very much like you are giving it an impression of oversubscription, like how you go with vGPUs, vCPUs. This is how you can actually have vGPUs concept realized. Now this is 5 GB each from a memory compartment perspective. So ultimately you can go in any combination. Like here I am requesting for 1G 5 GB, so I am getting 1 vGPU along with 5 GB of GPU memory. And here I am going with 4 GPUs with 20 GB of memory. Now this remaining one, it's up to me whether I want to go in any specific combination. So this is where this can be allocated to tenant 1, and these can be actually given to multiple tenants depending on what they are requesting for. This is how it looks like. You actually specify limits here. 1G, 10 GB and 1 you are requesting. So 1 replica you are requesting, which means the pod that will actually be requesting this will actually have this particular configuration mapped to it. And from a time slicing perspective, this is the other strategy. So managed instance, multi-instance GPU was one strategy. Time slicing is another strategy. When we talk about time slicing, it is pretty much the context switching that we have been doing in CPU world. This actually means that you will be having some specific slices carved out, and in a context switching way, you can have different containers or pods keep on requesting the GPU resources. So pod A or container A will come, and then it will use the GPU for some specific amount of time. Then it will have a context switching done to pod B or container B and so on. This actually is a more flexible approach and is even more older than the MIG approach. So this has been getting used in the traditional systems for having GPU sharing achieved. And as I mentioned, context switches happen, which means there will be some certainly impact on the latency, because context switching is generally a costly operation. However, unlike the 7 GPU instance slices that you are having in MIG, this actually gives you infinitely many slices. So ultimately, this is more scalable from a multi-tenant perspective, but the only downside is that the memory isolation and cache isolation is not there in this particular model. So it's not fault isolated or memory isolated. That's one of the biggest drawbacks. The other is that certainly there will be some latency hit. This is how it goes like. You first have to create a config map. The config map will just have the time slicing configuration. Here we are saying there is one config block that is T4 time slice X4, and then this is X10. So this is replica, means number of pods that actually can share this particular GPU. So this is like it can support 10 pods. This can support 4 pods. So ultimately you can have four pods doing the time slicing for the same GPU. And ultimately you reference this config map and then have the configuration, like this is where you are saying this particular pod is going to have 1 GPU requested, but then the configuration will actually be loaded using the config map. How this configuration is getting loaded is because there is an additional device plugin that we have installed on Kubernetes. So for different GPU providers, there are different device plugins available. NVIDIA has a different device plugin available. Intel has something called as Gaudi. Then you have AMD with, I think, ROMC or something. So there are different plugins available. You will need to deploy based on your Kubernetes platform. This is the third popular strategy, which is called MPS or multi-process service. This is mainly for CUDA processes to share the GPU. And this is pretty much an alternative to the standard CUDA API. And this helps you with the multiple CUDA processes sharing the same GPU, very much similar to how time slicing works. The only thing is that unlike the context switching that happens in time slicing, that kind of context switching doesn't happen, but still it has shared memory space. So that's where the memory isolation is still a concern here. So it also can be configured in a very similar manner. You have replicas stated here as 4, and then ultimately you have similar kind of node selector and resource related configurations being specified in the pod specs. So these are some of the key areas from comparison perspective, but in addition to what we discussed in the previous talk, there are some more strategies that I would like to highlight. One is called the spatial partitioning. Spatial partitioning actually helps you go in a kernel opportunistic mode to have streaming multiprocessors targeted. So it's again sort of a hardware level isolation that you can go with, and that's where you can achieve some sort of GPU sharing, but those really are oriented towards the SMs. Then there is something called as adaptive or speculative scheduling. That generally works again using workload kernel level isolation. So that's where you can go ahead and partition the GPU in the, I would say, in a workload aware manner. But then when I say workload aware, it's not really aware of the Kubernetes network topology. It is not really aware of how a specific GPU profile should look like. It's primarily based on how your workload kernels have been designed. But if you really want something which is Kubernetes aware, which is network aware, because when we are talking about GPU sharing, it's not just about, okay, we want GPU, a slice of GPU, or we want GPU with some specific memory requirement. It could also be that you are in a data center, a private data center, which is based on bare metal, let's say. And then in that particular data center, you have your nodes spanning across a huge network. Some of the nodes could be located very closely to each other. Some of the nodes could be isolated or could be interconnected using NVLinks or using some sort of P2P GPU networking appliance or some sort of interconnect. Then in that case, you need to rely on some additional job orchestrators or schedulers like Ray or Slurm. So in Slurm, you can actually provide a constraint called NVLink, wherein if you have GPUs present apart and they are connected over interconnect, then you can say constraint equal to NVLink, and it will make sure that it is actually scheduling your workload on GPUs that are co-located or that are connected in your network so that you don't have any isolation. Likewise, in Ray, you can go ahead, use these techniques behind the scenes, and then have a topology aware or Kubernetes aware sort of GPU allocation done. So with this, I'll hand over to Samrat, my colleague, who will be covering some of the demos. Yep.
Right, thank you, Anmol. I see a couple of familiar faces. Thank you for joining again. So yeah, as Anmol mentioned, we gave the same talk in the Open Source Summit 2 days back. Anmol covered some of the techniques like MEG, MPS, and time slicing. But we saw a lot of pros and cons with each of the approaches as well. So that's where a project comes into picture called HAMI, or Heterogeneous AI Computing Virtualization Middleware, which is a CNCF-backed sandbox project. And it helps in, bypassing some of the limitations of what we saw with MEG, MPS, and time slicing. So basically, if I have to summarize time slicing and MEG, time slicing and MPS, they don't offer the fault and memory isolation, but MEG does that. But again, MEG is a little bit rigid, in which you can only have certain profiles, like 7 slices of a particular GPU. In some cases, some of the newer GPUs only support 4. So that's the constraint there. So it's not very flexible. So that's where this project comes into picture, where it allows us to request compute and memory, just like we used to do for vCPUs and the memory in the normal Kubernetes application. So this allows for fractional requesting fractional GPUs and using something called GPU mem and GPU cores. We have GPU mem -% as well if you want to do it based on percentage. So as Anmol mentioned, we have this custom or resource extender model where we request in the MIG world or MPS time slicing world, we used to do nvidia.com/GPU equals to 1, right? So here we do something similar. We use the same resource model, but we use GPU mem for the memory and GPU core for the GPU compute cores. So in this case, I'm requesting 4 GB or 400 MB of memory of a particular GPU. So it's the same way, but the thing is, it enables that fractional thing I mentioned. And what it enables you to do is, it helps you in efficiently utilizing the underlying GPU, which the previous 3 approaches that we saw might not fit some of your use cases, right? So if you go with Hammy and you request fractional GPU, the good part is you also get that memory and fault isolation as well in the backend, and we will dive how it does in the backend. But there's a component called Hammy core, which intercepts all the CUDA runtime API calls and then makes those calls on behalf of the application which requested the memory and the GPUs or GPU cores. So that's Hammy, but there are other similar tools available. I'm not sure if you have heard about RunAI or Volcano. They do the same thing, which enables you to request fractional GPUs. But moving on to the architecture, so basically Hammy has 4 components. One is the automation webhook, the scheduler, the device plugin, and the Hammy core, which is the resource controller, in-container resource control, which is actually responsible for the CUDA API calls, right? So first thing, whenever you schedule your pod using pod spec, so what happens is the admission webhook comes into picture, and that adds the annotations and all the environment variables which are needed, and then the Hammy scheduler works in collaboration with the default Kubernetes scheduler, and both of them make the decision. So Hammy scheduler makes the decision of wherever that 4000 MB of GPU is available, it tries to schedule on that node, and then the default Kubernetes scheduler also comes into picture, and then lands that particular pod in that particular node. So that's what happens in the backend, and once that is there, then so we have this device plugin model, and what this model used to do is, so the idea was to create something uniformal standard, so that you can any vendor can go ahead and then add in support for requesting their particular device, right? So in this particular talk we are talking about GPUs, but Ascend, Huawei, NPUs, TPUs, everything is supported through the device plugin, right? And once the device plugin does its job, then the Hammy core is the actual thing which does that, which intercepts that CUDA API call on behalf of the application, and that actually sends the request and then enforces those limits of those fractional things that we are talking about. So that's the high-level architecture. There are a lot of things going in the backend as well, but it comes with a lot of other features as well, like scheduling policy is one of them. And basically what this feature lets us do is schedule pods based on some kind of whether I want the pod on the same node or I want the pod on the same GPU, right? So this helps you in enabling multiple use cases, like if you want fault tolerance or less, or you want to increase your blast radius, then you will schedule it in a way on different nodes, right? And similarly, if you want to use the GPU so that they are fully utilized, then you would want to place the pods on which already there are some pods, right? So we have 2 ways, node level and GPU level. So this is the annotation that you can use, which is node-scheduler policy. And we have basically 2 ways, bin pack and spread. Basically, bin pack says that, okay, land this particular pod on the existing nodes where already something is running. Spread says, I don't want to land that on any node where something is running. So this is for improving the blast radius. And the next one is for GPU, same thing, bin pack spread, but the only thing is this will land the particular pod on the GPUs which are already being used, and spread means which are already not being used. So that's the high level of scheduling policies. This is how you can do it. So if you see line number 6, 7, that's where we can add the annotation. This one is saying that okay, spread the nodes, so land those in separate nodes, but GPU wise use the same GPU on that particular node where already something is running. And then you can see the limits that I have enforced here. So GPU cores here saying that I need 30% of the GPU cores of a particular GPU. We have another feature in HAMI called task priority, where you can mention that okay, this is a particular high priority task, so whenever this comes up, then preempt the previous task, low priority task. So it's not that much flexible because you have to set this environment variable CUDA task priority. It's either 0, 1. So 1 means 0 means high priority and 1 means low priority, and it will evict any pod or pause them for some time until the the high priority task finishes. So that's the second feature. But if I have to quickly compare HAMI versus the other GPU sharing strategies which Anmol shared, the only difference is you see that isolation model where HAMI is software based, but it enforces those memory and fault toleration as well in the backend. So that enables you to be much more flexible in how you utilize the GPU, and so that your one workload doesn't affect the other, just like it does in the case of time slicing or MPS. So that's the only thing that I want to cover. But yeah, it has support for all the particular GPUs. Now, one good thing is it's heterogeneous. The H in HAMI stands for heterogeneous. So it's not just GPUs. It also supports NPUs. The support for TPUs, Google TPUs are not there yet, but there are plans to do that. So moving on. So you can scan this QR for the. I have this at the end as well, but we have all the snippets, whatever I'm showing on this GitHub repo. But let me quickly go ahead and then show a quick demo of HAMI. So basically, HAMI, in order to install HAMI, what you have to do is you have to first label your nodes appropriately with a key of GPU and value of on, as you can see on this one. I have one node with one GPU here. I'm using A100 in the backend, NVIDIA A100 in the backend. And I've already gone ahead and installed HAMI using the Helm chart that they have. And basically the components that we talked about, that's where you will see, which is the device plugin and the scheduler. So it creates its own custom scheduler also, which is responsible for finding the right GPU for the right pod. And we can see the device plugin as well. So I was running this on GKE, and I had to do some host level changes as well, which I'm not showing in this demo. But I had to change some or create some files for the CDI, etc., using the CTK, NVIDIA CTK on the host. But I'll not dive deeper into that. But I've installed HAMI here, and now what I'm doing is I'm creating the pod using the old way which Anmol mentioned, which is using this resource extender, using this resource model nvidia.com/GPU as one. Now this is utilizing the entire GPU. As you can see, it's running. Now what I'll for the demo do is I have a couple of other manifest files which are in the backend HAMI based, but I'll try to run them, and you will see that they will go in pending state because the whole GPU is fully utilized, right? So that's what I meant by underutilization, when this pod might not take the entire or consume the entire thing, but even though it's it's requesting the entire GPU. So what I'll do now is so here I'm showing that the HAMI file, which is the GPU memory, it's requesting 4 GB and the 30% of GPUs. So I have 3 similar files, 1, 2, and 3. What I'll do is I'll delete the previous pod, the old one, and then you can see that the pod that I ran earlier, it found the the empty GPU where nothing was running, and then it scheduled it. Now I'll go ahead and then I have the same files 3 times. I'll go ahead and then apply them. So what you'll see is all of them will successfully come up because Hammy in the backend is doing all those scheduling, the CUDA API interception, using symbolic links, injection, etc. And it's requesting 30% of the cores and 4 GB of memory. So you can see that we are able to do that fractional thing very well. I'm not showing the NVIDIA SMI command here in the demo, but if you go to the pod and run NVIDIA SMI command, you'll see that that's what is being allocated to that particular pod. And if you go on the host, you'll see that 3 things are running on the same GPU, but requesting different or separate memory and cores. Now, if I apply the 4th file I just created here, you'll see that that will go in pending because I've utilized all the virtual cores, right? 30%, which is 90%, right? So this one needed another 30%, it couldn't, and then it went into pending state. So I only had 1 pod. If I would have had another separate pod, then it would again come up. But if I describe the pod quickly, you can see it's using Hammy scheduler to find out the appropriate node for the appropriate pod, right? So that's what I quickly wanted to show for Hammy. Now, if I proceed forward, device plugin, if you think about it, it's still very rigid in a sense that you tie that resource model of nvidia.com/GPU or GPU mem, GPU core with your pod. So it's not flexible in a way. It's very tightly coupled with your pod spec. So that's where DRA or dynamic resource allocation comes into picture, which allows you to decouple the pod spec with the device that you are requesting for your particular pod. So now this will definitely, this is the future of device management on Kubernetes. So yeah, as I mentioned that it's a new flexible way or a claim-based way. So think about it as a persistent volume that currently you are doing in Kubernetes, where you create a persistent volume claim that creates a persistent volume in the backend, and then you use that claim in your pod spec, right? So that's what it does. It's very similar to persistent volume claims, and it decouples your provisioning of the pods with the device, right? So I know I'm out of time, but I'll quickly take another 5 minutes and then finish this. So what this enables is, you can request, flexible, GPUs or some, for example, if I have a GPU of 40 GB, then you can request 16 GB of memory from that. And then native sharing is enabled, like, here you can have multiple pods sharing the same GPU. So you can have 2 pods sharing the same GPU, or you can have multiple containers in the same pod sharing the same GPU. So that all combination is supported with a DRA and decoupled cycle that I mentioned. So this is the one of the major advantages. So you can just throw away the pod, the claim will still be there. So another pod comes up, you can just tie back to the same claim, right? So that's how it's not dependent on each other, just like we had it earlier. Now, how it does is I already explained persistent volume claim. So here we have something called resource claim template, which uses device class. So what device class is, for example, NVIDIA. For NVIDIA, it's gpu.nvidia.com, and a particular operator has to, make this available, or a platform team or someone, right? And then the resource claim template is what will be consumed by the application developer or the app operator, and they will have to mention this gpu.com in the device class of their resource claim template. And in the backend, it will create a resource claim. You can also create the resource claim on your own, but it's good that you create a template and then the resource claim will be created by Kubernetes. So this is what I just mentioned, which is you create the claim template, and then the resource claim will come up, and if you mention it in your pod, that will just assign it. So here on the right hand side, you can see the template, and you see line number 10. That's where I'm mentioning the device class name. Now that can be any other GPU from any other vendor. But here, on my machine, it was the NVIDIA GPU. So I had that DRA driver installed for NVIDIA GPU already. So yeah, you have to install the DRA driver for that particular vendor. And then if you take a look at the port spec on the left hand side, now I'm just using resource claim on line number 12. And then on line 14 on the left hand side, I refer that resource claim template which I have created on the right hand side. So this is how DRA enables much more flexible and powerful API compared to device plugin. Now there are again HAMI versus DRA we can do. HAMI still doesn't support DRA, but there are plans to support it. But HAMI again does that fractional GPU request really well. Now another disadvantage is that it has its own custom scheduler, which you have to install, which might not be it might be an overhead, right? And again, as I mentioned, so user requests using the resource model nvidia.com/GPU, and here in DRA it's mostly claim based. So I'll quickly go through some of the key takeaways, which is Kubernetes, as Anmol was sharing, that it is not or it was not that great at efficiently utilizing the GPU. Still active workings going on. DRA still is in beta in Kubernetes 1.3.2, but still it has a long way to go. How it efficiently uses the GPUs and how we are requesting it. HAMI solves that fractional thing, but it again uses the device plugin model. And DRA HAMI might adopt it in future, and that will be the real game changer in how we request fractional GPUs, because as we saw that it decouples the pod lifecycle with your device lifecycle. So that's all I had. These are the references. We will upload the slides on the the show the show notes, or yeah. So I know we extended by 10 minutes, but do we have any questions? Yeah, please go ahead.
Is it possible to run the HAMI project alongside an MIG?
Yes, that's possible.
Like
Yeah.
also on the schedule with HAMI inside of the MIG slices.
HAMI inside of the?
Instead of the slices of the multi-instance GPU slices.
Oh yeah, you can do that. So HAMI can be coupled with the MIGs, and inside the MIGs you can request those multiple GPU core and GPU mem. So that permutation combination is possible. Yeah. Yeah. Right.
Is the HAMI also fault tolerant? Like if some task will fail in the GPU, if the other task will also fail?
No. So that's where the HAMI core is responsible for giving you that memory and fault isolation. So even if that fails, unlike time slice or MPS, if one process fails, it takes down the entire GPU with that particular process. Right here, it gives you that strong isolation, the hardware, the resource isolation. Right. So you can connect with us on LinkedIn or Twitter, and if you have any follow-ups, we would love to hear. But thank you so much. And I know this was the last talk, so thank you so much for arriving and giving us your valuable time. We really appreciate it. Thank you so much. Yeah.